This is a nice paper because it looks at past data for weather extremes and crop yields to find relations and show that hot and weather extremes during the growing season have affected crop yields systematically across the globe for various cropping systems, maize, wheat, rice, and so on. And it also shows the trend in the co-occurrence of hot and dry weather extremes. They also look at wet and cool extremes which don't show a very systematic signal in their analysis. Instead of looking always into the future and saying what things will go wrong, it's always interesting, and I find them exciting to look at papers which are analyzing historic data, because then you can go back and take the models which are reproducing the past hot and dry weather extremes or cold and wet weather extremes consistently with the observations, and then see what they say about the future rather than simply jumping to the future from the outputs that are available. So this is much more common to look at future projections rather than historic events or the model consistency with the historic events. So the abstract says, although extreme weather events recur periodically everywhere, the impacts of their simultaneous occurrence on crop yields are globally unknown. In this study, we estimate the impacts of combined hot and dry extremes as well as cold and wet extremes on maize, rice, soybean, and wheat yields using gridded weather data and reported crop yield data at the global scale for 1980 to 2009. Our results show that co-occurring extremely hot and dry events have globally consistent negative effects on the yields of all inspected crop types. Extremely cold and wet conditions were observed to reduce yields globally too, although to a lesser extent, and their impacts being more uncertain and inconsistent. Critically, we found that over the study period, the probability of co-occurring extreme hot and dry events during the growing season increased across all inspected crop types, wheat showing the largest, up to 6-fold increase. Hence, our study highlights the potential detrimental impacts that increasing climate variability can have on global food production. These are the variables they use: hot days, dry days, wet days, cold days, average temperature, average soil moisture, total precipitation, and total precipitation for the whole year, and crop yield anomalies from these various sources that you can find references for, like the European Union reanalysis, the European Center reanalysis, So the variables of the main analysis and their sources shown here. The variables were calculated for each crop, year, and grid cell. For hot and dry or cold and wet days, we calculated the days above or below 90th percentiles for temperature and soil moisture deficit across all years. All indicators were calculated for the growing season except one precipitation indicator, which was calculated for the whole year preceding the harvest. Okay, the first figure itself is basically showing the model performance and its ability to capture the observed crop yield changes in response to the weather for wheat, maize, soybean, and rice, and the explained variance. So if you have a data set and you're fitting a statistical relation between weather and crop yield, and you have to say how much of the crop yield anomaly is explained by the weather anomaly, which is important. And you also have kind of a testing period and a verification period, which is also done. So all the standard ways in which these things are done, and they used a model called XGBoost regression model, which you can look up in the references. So here we are with the global mean showing wetter climate going from quartiles of 20 to 80 in precipitation, and warmer climate going from quartiles of 20 to 80 or 100, obviously 0 to 100 in terms of quartiles, so just be mindful. For temperature, so you are looking at wheat, maize, soybean, and rice here, and you're looking the corresponding maps with the global numbers shown here and the percentiles shown in the brackets. So wheat, you can see that in this corner you have dry, cool anomalies, and in this corner you have dry, hot anomaly, and here you have wet cool anomaly and wet hot anomaly. And you have the range occurring in between for various ranges of wetness and hotness, and you can see that the explained variance is a percentage of crop yield variability explained by the regression model varies from very low in these light colors to very high, above 50 in these darker colors. And you can see that wheat in the breadbasket of the US, in large parts of Eurasia, and also over China here, in Australia, Africa, and South America, and especially the breadbasket of India as well in the northwest corner here. And these are all explained variances, so it's just confirming that the model works reasonably well in many places where the explained variance is reasonably high in terms of the relation to dry and wet, dryness and wetness. Similarly, for maize, you can see the different regions light up here. So the corn belt of the US as opposed to the wheat winter crop, and similarly in different parts of India, Europe, China, and larger parts of Africa than for wheat, for example, as well as for South America. And this is now explained globally 50% with a range of 38 to 62 in terms of quartiles. And you can see the story for soybean here. Again, depending on where it's grown, you can see the concentrations and high explained variances. Some spot here in India, parts of Eastern Europe, and large parts of China. China continues to be big producer of soybean, as well as some South American countries and some Central African countries as well. Rice, which is obviously large for South America and Asia, show that explained variance in terms of rain and temperature are not as high as some of these other crops. Okay, so it's highly protected against wetness with flood irrigation and so on. So you expect the sensitivity to temperature and wetness being somewhat less for rice, but you can read up the details in the paper. Looking forward, global results about the relationship between crop yield anomalies and the number of hot and dry or cold and wet days during the growing season. Results are shown for studied crops, again wheat, soybean, and maize and rice. Here the number of hot and dry days or cold and wet days refer to days during the growing season above the 90th or below the 10th percentile for temperature and soil moisture deficit respectively, i.e. extreme indicators are calculated separately for each growing season. The results are based on partial dependencies calculated separately for each extreme scenario from the XGBoost models trained at the global scale. Uncertainty of the results was evaluated by calculating the partial dependencies 100 times while sampling the years in each training and validation set. So there is a kind of a bootstrapping method which produces data from the given time series to test again and again. The violin plots describe the range of estimated crop yield anomalies across the model runs in a situation where respective weather anomalies are fixed at 1.5 sigma standard deviation, while the heat maps described averaged impacts across a range of hot and cold, cold and wet scenarios. Okay, various ways in which these exercises are done. So looking here at the global results, so no maps here. So you can see that again, as the number of hot days increases from 0 to 1 standard deviation and 2 standard deviation on the hot side and 2 standard deviation on the cold side, and similarly number of dry days going to -2 sigma to +2 sigma, and here you have number of cold days and number of wet days. You can see that in the dry and hot day corner here, the yield change is positive in all these crops and also in this map, but not as consistent as here. And as you go to the number of dry days and number of hot days, this corner lights up with the largest number of percentage of crop yield change, so being negative. Okay, so again the message is that the wet and cold days show some impact of losses. You can see in each of them there is some brownish colors, but it's not as consistent as the hot dry days that are looked at. So the lower number of dry days, lower number of hot days are resulting in a crop anomaly that's positive, and if you go towards number of dry days being larger with hot days being larger as well, the simultaneous occurrence of these weather extremes gives you the largest crop yield losses exceeding 5%. Okay, so you can look also for the wheat, each crop here. You can look at the what they call the violin diagram. You can see that the numbers are all negative, so you have hot and dry being the most negative here, hot and dry being less and less negative, cold and wet being negative, but cold and wet separately being less negative than any of the hot and dry combinations or individual extreme events for each of these crops. So you can see that the impact of cold and wet days with cold and wet separately are also not as consistent as for the hot and dry days, as we already said. The third figure shows the relationship between crop yield anomalies in percentage and co-occurring hot and dry and cold and wet conditions during the growing season for each climate bin. Results are shown for studied crops, again wheat, maize, soybean and rice. Map and divisions etc. are shown in the supplementary figure. You can look up here. The number of hot and dry or cold and wet days refer to days during the growing season above or below the 90th and 10th percentiles respectively for temperature and soil moisture deficit respectively, i.e. extreme indicators are calculated separately for each growing season. Okay, the results, which are based on partial dependencies calculated from XGBoost models trained for each climate bin separately, estimate crop yield anomalies in a situation where the number of hot and dry days deviates from 1.5 sigma from the long-term average. Uncertainty and confidence intervals of the results were evaluated by calculating the partial dependencies 100 times while sampling the years in each training and validation set. So it's all good that the paper also worries about uncertainties and dependencies on various parameters, so confidence is also verified that way. The mapped value is the average of the 100 crop yield anomaly estimates obtained. However, if 0 was within the 95th percentile confidence interval of the crop yield anomaly estimates, the mapped yield anomaly estimates was also set to 0. The maps presented in the figure were used, calculated or created using these Python modules. Okay, again just consistent now with the map showing hot and dry and cold and wet anomalies for each crop, wheat, global means, and in these maps and the distributions in these maps. So all these regions which are big producers of wheat obviously have to worry. India here for wheat shows slightly positive or basically 0 value here, but China has lots of brown colors here. And similarly maize, you can see the main point is that most of the colors across for each crop are brown, so the values range from close to 0 to minus 7.5 or greater in terms of percentage yield change, which just re-emphasizes the caption of the article that hot and dry extremes are bad news for crop yields for all these crops, which are really staple crops for most of the global south and also big suppliers like the global north. So they are used for animal feed, not just human feed, so the cascades of crop yield losses can go into price of meat and then also various other things like ethanol and so on, depending on which crop is getting affected. Again, the story is that the cold and wet extremes do not have a very consistent signal across the globe. As you can see, the colors here are much darker and much more systematic in terms of the dependence on wetter climate and warmer climate. That's not so systematic here in the wet and dry phase space here. Okay. Finally, historical evolution in the probability of co-occurring hot and dry conditions during the growing season between 1980 and 2009. Results are shown for studied crops, again wheat, maize, soybean and rice. Here a grid cell is considered hot and dry for a specific year if the number of both hot and dry days during the growing season deviates by at least 1.5 standard deviation from the long-term average. So now you are kind of computing a compound event of hot and dry weather extreme. The number of hot and dry days refers to days during the growing season above the 90th percentile for temperature and soil moisture deficit respectively, i.e. the extreme indicators are calculated separately for each growing season. The historical evolution of the probability in co-occurring hot and dry events was assessed by logistic regression. For the global results, event frequencies were calculated as a percentage of hot and dry events for each year and as a 5-year average, whereas the uncertainty interval for the regression lines in the figure were calculated by bootstrapping, so creating 100 samples, bootstrapping the observations, and plotting the regression line for each sample in gray color. For the climate bins, the trend obtained from the logistic regression are represented as odds ratios. If the odds ratio is above 1 or below 1, the trend is increasing or decreasing respectively. Note that if the trend was statistically insignificant, where p-value is greater than 0.05, for any of the statistical tests conducted, the reported odds ratios was set to 1, i.e. no trend. Okay, so basically the message is that if you look for each crop and if you look at the again climate being drier, hotter or wetter and colder, you can see that the trend is mostly increasing. The colors are mostly all gray, brownish for all growing seasons. The growing seasons are not the same in the year, so we have to always worry about that, and the confidence limits are shown here and the number of samples are shown here as well. So you can see that the probability estimate and observed frequency of events in percentage for wheat, maize, soybean and rice with the years shown here. It's basically bad news, and obviously now you can go find a model to see if the model reproduces these observed changes in hot and dry extremes co-occurring, and then see if that model projects something getting worse into the future. Okay, in general, no good news here, but at least we should be aware of what the co-occurring hot and dry events do. This also gives us a way to create early warning systems where we don't just look for rainfall anomalies to manage, let's say, irrigation, water and so on, but we also produce early warnings of temperature and hot extremes occurring together so that crop yields can be monitored. At least the dry part of the extreme may be easily compensated for by irrigation, but of course that means either groundwater mining or some other way of exploiting water resource, but nonetheless at least that can be used to save crop yield losses. Okay, so I'll leave it here, but it's a nice paper that you should read up if you are interested in more details. Also has a lot of nice references which I didn't use here, so please follow up if you want. Okay, thanks.